Okay, this is our last week. We are gonna do some for the next 2 days. We're gonna do some boards go up, please, where we rock through some of these problems here from last year's test on chapter 7. We've done a handful of problems like number 2. That's what we're gonna start with today. I don't think we'll do anything besides that today. And then we will go and we'll do problem 1 and problem 3 here. Problem 1, like this is one that I kind of stumbled upon just by people asking questions way back in the day. And I think it's a super cool um, uh, abstract phase plot problem that is just like it's fun to do for me. Maybe there's something wrong with me, but for now we are going to do one like this. This is like what you've been doing. I got two populations, X and Y. X and Y are represented of the size of the population. Um, I want you to find the phase plot for this thing that describes the system, or that tells us what happened with the system. Um, and then if you are able or willing to try, I would like you to explain in a few sentences what is happening at each critical point and also what is happening in the system as a whole. So go ahead and do that. This is like exactly what I would be doing if we were in school, getting ready for a test. I'm not going to give you a test on this. Your grades aren't going to change. We're just doing this for fun at this point. Um, and after this week, we're done. So maybe you guys already watched my little goodbye video. So I hope you did not go watch it. Anyway, so hit pause, go ahead, do this, and I will walk you through it on the other side. Okay, here we are. We'll skip over that. All right, here we go. So that's what the phase plot looks like. We get a saddle, a source, a saddle, and a spiral sink, I think. Um, so uh, my thing factors to this, x factors, x prime factors that, y prime factors to that. We can pull that 4 out, which is nice. Then I got these guys. 0, 0 is a critical point, like always. 0 makes that 0, so 5. And then when the y is 0, that makes this 0. So for x, that's 20, so that gives us 20, 0. And then this one we get by solving this system. Let's see, we could do it by hand, or you could use RREF. Here's a Jacobian right here. And then which is just some partial derivatives. From there we go and we plug in each of these critical points to that Jacobian matrix to linearize that system. So 0, 0, we get this one. 0, 5, we get this one. 20, 0, we get this one. 10, 15, we get this one. The first three are all triangular matrices, so the eigenvalues are the entries on the diagonal. So this one is 60 and 20. It gives me 1, 0 with the 60, 0, 1 with the 20. That's nice. It's a source. We get this guy. 0, 5, I get saddle because I got a positive 15 and a negative 20. The negative 20 is the flat vector. Sorry, is an up and down vector, a vertical vector. And then we get this little diagonal vector right here, the 7, 2 on that 50. Over here, we get almost the same thing. I won't go through the details. You can see it there. I would just repeat what I said there, except for it's flat instead of vertical. For this 10, 15, we get this guy. This is one we got to do some work for. You get this thing. And then when you do the Pythagorean theorem, or sorry, not Pythagorean, quadratic formula or completing the square, whichever you want to do, you get imaginary numbers. So we stop there. Oh, we get imaginary numbers. We get a complex number with a negative real component, and that imaginary component that we don't really care about, it is a spiral sink. So I put these 4 pieces on this phase plot in the appropriate spots. The spiral sink is here. So what happens? We go up and then we sink in. We go in and we sink in. From here, we'll go out and in. From out here, we would come in. From here, we come down and in. You could totally have it go like this, loop around like that. and then have this loop in like that, and then build your spiral around like that, and that would be totally legitimate. I'm sure we could test some values to figure out which direction it goes, but this is good. Or if you did the other spun the other way, I guess we could say it's good. In terms of the general what's happening, this is a peaceful coexistence model. I don't know how much we've talked about that this year in terms of how to identify all of them. I've got two species, X and Y, and they have a shared carrying capacity here at what value? 10, 15. At 0, 0, if there's no X and no Y, if there's no X species, then the Y will go up. If there's no Y species, then the X will go up. So that's like the growth rate by itself. They each have a individual carrying capacity. This one's at 20. This one's at 5. Um, so let's talk about them at that 20. This is the carrying capacity for the X species. It'll either sink in that way, or sorry, it'll go up that way, or it'll sink in that way. If I've got a little bit of Y, then it'll go in, and then eventually, as we get close to this carrying capacity, we'll slide in there and go to the shared carrying capacity. This thing's the same thing. So, I could repeat what I said there. And then 10, 15, that is the shared carrying capacity when both X and Y are there. So hopefully you are able to do that phase plot and you understand this contextually in terms of these shared, these two species. Now, I challenge you to think, what would it be like if I had a third species? What would those look like? I would have to do a phase plot in 3 dimensions, and how cool would that be? What if we had 4? Well, we could do the math behind it. We can't create a phase plot because it's just impossible, but we could do the math behind it and analyze it. So, anyway, I will do the other two um, on Tuesday, and that's the last thing I will ask you to do for me. So, thank you. Hope you all are well, and I will talk to you soon.